There's an old saying I learned from Paul Hilfinger that I brought up earlier in the class that an engineer will do for a dime what any fool will do for a dollar. In 61A, you guys learned to be fools, how to build programs that do pretty much anything. And in 61B, we've slowly been accumulating tools to be able to do things more efficiently. So efficiency comes in two different flavors. One of those is the cost it takes you as a programmer to complete the project, right? That's the time you need to spend or the time others need to spend to build something. So what does that come down to? Well, it comes down to how hard is it to not just write your basic implementation, the kind of things that we focus on in 61A and 61B, but also how hard is it to read your code, to modify it, and also how to maintain your code, how to make sure that it keeps doing the thing it's supposed to do. And maintenance isn't really necessarily bug fixes or like bits that got flipped by accident or something like that. Instead, it's mostly tweaks and improvements. You get some more feedback about how your code should be behaving, and you adjust so that it does those things. And so I'll make a note that most of the cost in a program is not in its development. It's not that thing we do in 61A and the 61B where we're hammering out our code and finally we push a button and a sound appears and we're all excited. That's not where most of the cost is. Most of the cost is in making sure that the code is maintained. Okay? And so we've talked a little bit about ways we can, up to this point in the class, how to make code more readable, modifiable, maintainable, and I guess writable. And then there's also execution cost. How long does it take a computer to move all of its electrons around and get the program to actually execute? And the other side thing with efficiency, but often not quite as important, I mean, it depends on your application, is how much memory your program uses. Okay, so we're going to focus on these starting next week. And so I just want to wrap up what it is that we've learned so much about programming so far about programming cost. Okay, so there's some Java features, and this isn't an exhaustive list, but just to contrast Java with other languages you might have seen in the past, we had some features like packages, the idea of packages, the idea of static type checking, the idea of inheritance. So if it were a live lecture now, or you could appear in my room right now and I could speak to you as a ghost, we would go through this, but instead I'll just give you my pre-canned answers that I have from last semester. So packages, what's good about them? Well, it's great because it helps keep our code organized. It gets them into folders so that if I'm looking for the josh.ug.animal class, or well, other way around, it's going to be in josh/ug/animal. It also gives us canonical names for classes. And in that sense, we don't have to worry that maybe I wrote a class called dog and someone else wrote a class called dog and there's conflicts because each class has a canonical name that identifies it in a more thorough manner. The bad part is it's more work, right? To be able to compile and run packages, we have to first understand what packages are. They could be a little annoying to work with from the command line, as you saw in homework 1. But on the whole, once you know what you're doing and you're using the right tools, packages are just a good idea. Okay? Also, static type checking. What's good about that? Well, it speeds up your code. Because Java doesn't need to actually at runtime do type checking, your code will tend to run faster than it would in other languages. And it also lets us catch certain errors early, right? So before anybody even runs the code, we try and compile, and it says, okay, you cannot, so Java has the feature that every expression, every variable, every return type has a declared type, and they have to be compatible. And so the compiler could check any errors where there are incompatibilities, which is nice. And there's some other ancillary issues, like how arrays are stored. So if everything is the same size, then you don't have to worry about, 61. Now, the bad thing, of course, is it's more verbose. We can't just write one max method that takes anything, like take the max of x and y, compare them using greater than, and you're good. Instead, we have to do things like resort to generics or rely on interface inheritance to have a compare to method. So one of the obvious and big downsides is it makes it harder to write code. So if your job is to get something out the door really quick, Java could be a little slower. But the nice thing is that down the road, 2 or 3 or 5 or 10 years from now, because I have all the types declared, your code is more narrative. You can read it. You can say, someone gave me a map from integers to strings. I know that's what I'm getting. It's not going to be something else, right? Inheritance. Well, we have the notion of implementation and interface inheritance, and those are good because, well, interface inheritance, it allows you to have subtype polymorphism. I can give you an object of type map, and I can hide all the details that it's secretly an array map or a hash map or a tree map or whatever. It just does map stuff. And whenever you call the method, it does the right thing. And you don't have to be thinking about the underlying data structures, which is incredibly important. It allows us to hide details, one of the absolute most important things in programming. And then implementation inheritance allows you to reuse code, right? So suppose I have an interface that says, you're a duck. You need to be able to walk, fly, swim, yada, yada. Well, when I have now a Mandarin duck, let's say, for example, it also needs to know how to fly, walk, swim, and so forth. And so implementation inheritance allows you to not have to define those verbs, those methods, those things that Mandarin duck can do again inside of Mandarin duck. Instead, you already got them from duck. Okay. Now, the bad side, of course, is that if you're just relying on interface inheritance, if you don't have default methods in the duck class, then it means you have to implement all those features. So you may end up having a bunch of very similar fly methods for each of these ducks. And it may be some of the interfaces in Java have 40 or 50 methods, and it can be a little annoying sometimes to write, say, a new collection, which is a java.util collection. It can be harder to understand code because it doesn't quite flow in that beautiful narrative way. I'm going to call this function, and these are the things it does, and so forth. Now, there's a little bit of extra thinking you'll have to do. You'll have to say, oh, well, because of subtype polymorphism, because methods can be overridden, maybe it's going to jump around to this class and that class. So it could be a downside. We won't necessarily run into that a ton in 61B because it's not like a huge object-oriented programming class. I mean, it is, but it's not the size of the projects you'll see out there in the real world, but this can be an issue with larger projects. And so we'll talk a little bit more about that in a little while. Okay. So as far as keeping programming costs low, all right, these are some big picture items. Instead of just these Java features, let's just discuss the big ideas, right? So modularity is a very important idea we've talked about. How do I take my programs and break them into easily understood subproblems? I want to build a train. Okay, well, then I need to figure out how to roll the train with wheels. I need to know how to create power in some way, right? I burn coal or something. I need to be able to transmit the power from the coal-burning engine, let's say, down into the wheels, that kind of thing. So we break it into these subproblems, and that allows us to do big things. And so that happens in programming as well, and you'll be seeing that in spades in Project 2. We have the notion of invariance, and we didn't harp on it so much, but we basically said whenever we're calling functions, when we're running methods of some data structure, or when we're running an algorithm, there are certain facts we want to maintain true. So we had that example of selection sort. With selection sort, it should always be that the smallest item is on the leftmost side of the, or the 0th side over here in the array. And that notion of invariance, we'll talk a little bit more about it, particularly when we talk about recursive data structures. But many programmers will only be considering these invariants implicitly. You do whenever you're writing code, but sometimes programmers actually write them out explicitly. But just the idea, the fact that we have the word invariant can make it nice to be able to communicate to other computer scientists what it is you're trying to accomplish. Testing, well, we talked a bit about the idea of writing your own tests because you don't want to rely on autograders because at some point they won't exist anymore. And so what you could do is create automated code verification tools that try to give you the suggestion that your code works, right? It doesn't necessarily, it's not 100%, but you run those tests and you see, okay, good, seems like my code may well work. Now I'll mention just actually as an aside that it's impossible to write a general tool that just verifies code correctness. There's actually a major field of CS research, which is how can we write out a specification that we can then validate against or use to validate some code. In fact, it's in general, like if you wanted to write a general purpose one that does anything, that's impossible. In fact, it's not even possible to prove that a particular piece of code won't go into an infinite loop. And so if you're curious about that, you can read this, but it's some kind of fun, deep math. Okay. Another idea we talked about was the notion of modules and encapsulation. This is actually just a slide from before. But remember that a module is a set of methods that work together to perform some task or some set of related tasks. Like, for example, a renderer for Project 2. And so we'll say that a module is said to be, again, encapsulated if its implementation is completely hidden and you can only access it through some nicely documented interface, right? So if we have an abstract data type like a stack or a map or something like that, it is encapsulated. You can't see all the goodies inside. You could just use the features that it gives you. So I have a class called xlist, for example, that can do these things here. I don't have to know whether it's based on an array or a linked list or whatever. This is an important idea. Okay. I guess I'll introduce this term API, which you may have seen used casually in the class occasionally, double occasionally, triple now. So the API, Application Programming Interface of an Abstract Data Type, is the list of constructors and methods, including an informal description of the effect of each. All right? So it's not a precisely defined term. Some people might use API in some slightly different way than what I'm using here, but basically it just says I have some data type, and I'm going to explain what all the things are, what all the buttons are that you can press. And so the API consists of two things. One is the so-called syntactic specification, and the other is the semantic specification. So the semantic specification is the part you write out in, say, English, usually, that just says, hey, this is what everything does. Sometimes people write them in some kind of formal language with special words they use, but not always. And then the syntactic specification is actually the code you write out, right? And the compiler then, whenever you will verify that the syntax is met. So if you have, in an interface, the syntactic specification is basically public interface, yada yada, and the compiler will make sure that the syntax is good. Okay, so if we have an interface, we'd have an interface file. In Java's case, it's public interface potato. So the compiler checks the syntactic specification, and the semantic specification again is some document we're going to write in English. Okay, a little tortured, but I got through it. All right. So in the Project 2 design video, like I guess maybe we should look at one, or not. Okay, there it is. I gave an example of what a semantic specification might look like if you actually wrote one up. So implicitly, that's, the assignment specs are that as well. But in this case, and if you haven't looked at this yet, remember there's a Project 2 video that explains some thoughts I had about design. But yeah, so here's a semantic specification, which is explaining what each of the things you can do. Now this actually goes a little further because I'm showing here private things. In the API, that's for the world. You probably wouldn't actually include the private variables, but here I was including it so we could discuss how the data structure works. But each of these methods, explaining what they do, that's the semantic specification. Okay? All I'm saying basically though with the phrase, there's a semantic specification is somewhere you really ought to write down what everything's supposed to do. So this notion of creating an interface that you hide all of the details, right? That again, way back to like the first or second lecture, with a car, we don't let the user know all the little things under the hood that are happening. We give them something really simple, gas pedals, steering wheel, and so forth. But what's interesting about programming is that it's not just about hiding details from other people who might use your code, but from your own self, right? So the idea of hiding details, I've now underlined and bold, is I consider critically important. Having been to many office hours over the course of the last couple of years here at Berkeley, I find that this is one of the biggest differences between students who are having a good time in 61B and those who are struggling. Oftentimes, struggling students have methods that are like 200 lines long, and there's just so much detail, and you can't fit it all in your brain at once. It's really, really important to be able to break things down into pieces so that you are not thinking about everything all the way down to the bottom. Just not going to help. Okay. So how do you design an API? How do you decide where to draw the lines of abstraction? I would say it's actually really hard. One of the hardest parts about writing a program is deciding on the API, and that's actually what makes Project 2 hard. If we just gave you a bunch of methods and said, go implement these, this project would be not that big a deal, I think. I mean, there'd still be things you have to figure out how to do, but it's the API design that really makes this fundamentally difficult. That's the only time we're going to do that in 61B, by the way. I mean, you'll have a little bit of freedom in other projects because you'll have a public-facing set of methods, but this is the only time in this class, because it's an early class, where you're going to go through the whole process and just produce something that has a certain behavior with no constraints from us. Okay. Later classes will get a chance to do more. And so, of course, you'll find it's challenging, frustrating. You'll run yourself down blind alleys. And I just want you to see this now just once, even though I know it'll probably be a bit stressful for a lot of people. Now, I'll say that in the real world, whenever you design an API, the decisions you make are incredibly important, right? So if you go out there and you say, I have a class here, and there's a set of public methods and variables, I am saying that those methods and those variables will be available forever, for anybody, for all time. 100 years from now, it should still have the same behavior. So you're making a big decision. And a lot of the crufty things that are kind of ugly about Java are because of this. There is, for example, in the object class, a method called clone. I've never used clone. I honestly don't really know exactly what it does. It's a strange method, but it has to stay there. They can't just take out clone, because somewhere in some server that maybe is running a major piece of, I don't know, banking transaction, somewhere somebody has written code that uses clone. You can never, ever take it out. Okay? Now, it's actually also interesting. There's a current event going on between Google and Oracle, who are the owners of Java, the implementation that most people use, and the whole product that is Java. So there's a lawsuit where Google basically created their own implementation of some of Java's API. And I'm not going to go into the details there, but basically for the Android mobile operating system, they basically said, okay, well, we're providing something that looks to the outside world just like Java. It has all the same buttons, all the same methods. It behaves like Java. And Oracle said, well, we think this is copyright infringement. We spent all this time, effort, putting together this API. Because as you've seen with JavaFX, I mean, it is a tricky API to use. And it's still actually much better than a lot of other APIs out there for doing graphical user interfaces. So they basically said, this is our life's work. We poured so much energy. Well, not their entire life's work, but somebody's, right? Someone poured blood, sweat, tears into this thing, and Google's just going off and saying, okay, well, we're just going to write it, right? The hard part of Project 2 is designing the API. We don't want you sharing your API with your designs with everybody. We want you to really think about it. And in this case, there was a commercial example of this where Oracle said, well, I think it was actually Sun Microsystems who came up with the APIs in question, but they own it now. So they basically said, no, we don't think it's cool for you to be giving an implementation of our API. And so Google responded by saying, okay, well, even if it's copyrighted, there's a thing in the United States copyright law that there's so-called fair use, right? I can take a video of, I don't know, Joan Rivers doing something. Why Joan Rivers? I don't know. Do you even know who Joan Rivers is? Probably not. But I can take a video of her and do whatever I want with it, even if it's some piece of copyrighted material involving her, because I can be like, oh, I'm making a new piece of art out of it. And so obviously the boundaries can be a little blurry, what constitutes fair use exactly, but Google has basically taken that tack. And so this lawsuit about this, because of course it's ultimately about money. Google did not want to pay Oracle for something, I believe, was the issue. I'm not 100% certain. But the lawsuit started in 2010, still ongoing. But APIs, they're a big deal. Yeah. So I will mention at least whenever you're in the early phases of a project, the design of an API or the selection of data structures, hint, hint, Project 2, can be an iterative process. Okay? It's nice to get it right the first time. It's nice to be able to say, okay, I came up with the design, right? I came up with a document like the one we had, this one. I came up with a document like this, and it worked. It was beautiful. I just implemented it. There was no problems. The buffalo, the pythons, the ducks, and the hedgehogs all celebrated, and everything was fine. But sometimes that doesn't happen. Sometimes it's a little more work. And if you don't, right, if you hit some block where you realize, oh, my API is actually terrible for this process, and I'm going to have to write like 300 methods and pull my hair out and die. Rather than do that, sometimes it's better just to go back and kind of change the internals, right? And because your product is not world-facing at this point, you can kind of do whatever you want. Okay? So it may be the case that in Project 2, you hit a wall where at some point you have to rebuild some pieces. And don't feel bad about that, because you've learned a lot in the process. It's not the programming that takes a long time. It's coming up with the ideas that turn into the programs that's especially hard. Okay? So I'll give a little word of warning, just because this is a pattern I observe sometimes with 61B. If you start creating instance variables that look like this, which is valid, I want a map that takes strings and maps that maps strings to maps from integers to doubles. This kind of complex data type, whenever you're trying to specify one like this, it could be a sign that you need to hide something from the class using some map. So my little example here is, let's suppose what we're doing here is storing stock values at the end of the year for various companies. So I map a string to a map from integers to doubles. So in this case, FB, the string, maps to a map from 2012 to 26, 2013 to 55, 2014 to 78, 2015 to 104, and so on. Right? So if you were looking at the raw data structure, you're the person writing code that manipulates a table of stocks, then you have to be thinking about all this stuff. Whenever you're writing code, you're going to have like .get. It's going to look a little messy. So often this is a signal that really you should be doing something more like this. I want a map. I don't know why I decided to say hash map here and map. Doesn't matter. Just say it's map there. But I could say, let's take a map from a string to, in this case, a time series, right? Each of these things, if we think about what they are, we just step back. We just think, okay, what is this thing? What's a series of data over time, okay? And if there's certain methods that we write that are specific to time series, right? Like maybe I want to sum two different time series, I don't know. Then it makes sense to push all that stuff into another class, right? So I realize that my code's getting too big, it looks ugly, I have maps from strings to other maps, then I can kind of butt off this little piece and say, okay, time series, it's its own thing. And so now, the person writing the code that manipulates these things, the thing that actually has the instance variable sum map, when it looks, this is just a simpler picture to understand, right? FB, well, that's some time series. Amazon, that's some time series. Netflix, that's some time series. If I want to add new things to the time series, then I will call the add method of time series. Okay, so just a word of warning. This is what students who tend to do better in 61B do. They break things into little pieces. Students who are struggling often do this. They put everything out there in the open, and it becomes too complicated to read the code, to understand the code, and nobody likes it. All right. So some issues with API design. There's going to be a quote from Joe Armstrong coming. All right. So that's some potential pitfalls, other than the one I just saw, right? So it could be that you write an API that's actually too hard or impossible to implement, right? So you might say in my specification, this is a data type that you can insert numbers into any position, you can find any number in constant time, you can insert in constant time, and so forth. And it may not actually be possible to obey all the things you say. That's one issue. It could be too hard to use, so arguably JavaFX has this feature. The API has these very complicated things you have to understand, like get children and the root and adding things and so forth. And in that way, it makes it hard for, say, a programmer like yourselves to figure out how it works. If you have to have training just to use a specific API, often it's something you might consider too hard, but maybe not. Sometimes the task is just really difficult. It could be too general. So many of you guys will be tempted to write an editor class that does too much on its own. Where it's just maybe you only have editor.java. It is possible to write this program with only editor.java, but that's going to be horrible. You're going to have a set of methods, presumably, that are just a little too much. You can have too specific. Sometimes you can have methods where you have many libraries, sometimes you can have issues where you give methods that should be below some abstraction barrier. So matplotlib in Python is a classic example of this, where you can manipulate all these things like xtick data, and it just feels like something I shouldn't be doing. As someone trying to make plots, I shouldn't be manipulating these low-level details of the plots. There's some missing middle layer there. I don't know what it should be, but it seems not there. They could be too narrow. So our early version of slist had no getI method, and that might be something we want to do with an slist. It might be too wide. That is, it has too many methods. So the fact that we had a get method in a double-ended queue is a bit of a, I don't know, strange choice, really. I mean, we did it because we wanted it as a programming exercise, but if you look at implementations out there of what a deck ought to be, they often don't have a getI method, okay? Because it's a double-ended queue. You get in and out of line at the back. There's no way to look in the middle, just often, right? Or too wide. An example we'll have in a little bit is the so-called stack class in java.util. So there's a stack class in Java, and it's a little funny. Okay. So a helpful motto, thank you, Joe Armstrong, is to provide to clients the methods they need and no other. You don't want to give them other stuff they don't need. Okay. And all these things kind of come with experience, but wanted to give you a sense of different things that can go on. All right. So that's it for this first little part. And next, let's talk a little bit about, once we've designed an API, what it is like to implement them.